Angus. Yeah, special thanks to Angus, who's actually head of developer relationships at Mina. I let Angus deep dive a little bit about Mina, the ZK, which is the latest technology out there, which is a transformative technology in the blockchain at the moment. He's actually joining us from UK. Are you in Scotland, Edinburgh, or London, Angus, at the moment?
I am currently in Edinburgh in Scotland. So
okay. I've been there in 2018, so love the place. Sometime to visit very soon. Cool. So thanks, Angus, for taking the time and for the discussion today. Looking forward to have an exciting discussion about ZK rollups, what Mina is doing, and how the developers here can actually start building projects on Mina, and what are the resources and tools that are available for the developers to get started in the space. So those are some of the key points that we are looking forward to hearing from you. So one more special thanks to Rakesh, who helped in putting this together. We've known Rakesh for quite some time, more than a year. He's actually leading Mina in, he's the head of India for Mina. He has been managing most of the developer relationships and everything else. Now, if you have any questions, maybe we'll have Rakesh, PG, and other Angus information at a later stage. You can directly reach out to them as well. On that note, Angus, over to you. The screen is on.
Thank you so much for the introduction, Karan. I'm just going to see if I can share my screen with Zoom, because I've got some slides to show you. Let's see here. Share screen. Now, hopefully, can you now see my screen?
Yeah, we can see it.
Yeah, we can.
Okay. Good. That's a good start. I don't use Zoom often, so yes, thank you for the introduction. It's great to be here today to talk to you. It's always a bit confusing for me. Like Indian time zone is half an hour off, because usually when you deal with time zones, right, it's all on the hour, so you just convert like a whole number of hours to get the time there. But the Indian one, the Indian standard time is half an hour offset, which always makes it confusing. Sometimes I'm half an hour early or late, but we managed it this time. So yes, hello. You presumably all know what you're here for, but this is an introduction to Mina Protocol and Snarky.js, which is a TypeScript library I'm going to tell you about that you can use to build zero-knowledge applications. My name is Angus Maidment, and I'm here from the Mina Foundation. This is a little introductory slide. I'm wearing the hoodie there and blending into our background kind of banner at a conference. But yes, I'm doing developer relations for the Mina Foundation. So I'm going out there, spreading the word amongst developers like yourselves about Snarky.js and the Mina Protocol, and helping answer your questions, and also, telling people about what cool stuff developers are building on Mina. I am from Edinburgh in Scotland, and that's where I currently am. And you can follow me on Twitter to see what I'm up to and get all the latest updates about what is happening in the world of Mina. There's my handle. It's at blockchainbeard. So I probably should have put a QR code in there or something, but maybe next time. So yes, today I'm going to talk to you about the Mina Protocol and give you a brief introduction to ZKPs, zero knowledge proofs. And I'm going to tell you a bit about ZK apps, which is applications that you can build as a developer, which use these zero knowledge proofs. We're going to talk a bit more in depth about Snarky.js, which is the TypeScript library that you use to write these ZK apps. And then I'm going to tell you about ZK Ignite, which is a program that we are running, the Mina Foundation, and also some other ways that you can get involved and learn more, continue learning about Mina. So first of all, ZKPs, right? Zero knowledge proofs. Now, if you've been around in blockchain for a while, you may have heard the phrase ZK. A lot of people are talking about ZK or zero knowledge cryptography because it's very good for certain things that we need for blockchains, right? And so we're just going to have a quick introduction to zero knowledge proofs here. I'm going to tell you what they are and what you can do with them. So a zero knowledge proof you can prove something, and then someone else can verify information in a private, trustless, and decentralized way, right? And so that's good for a number of different applications. So it's things that we're already seeing and you may be familiar with already is things like ZK rollups and ZK EVMs. So that's more on the scalability side, where you're kind of, instead of doing computation and verifying it by repeating the computation, you do computation, you produce a proof, and then you verify that proof, which allows you to do more computation. It's also good for things like private transactions and private voting. So obviously voting is something that society needs people to do to continue functioning. And in the digital era, we're thinking more about how we can make that more private and more secure, right? ZK identity is something where basically this idea of identity in the digital world is something that a lot of people are having to think about. We're kind of redefining or rebuilding the idea of identity, right, with the internet and apps and digital services. So zero knowledge proofs can help us a lot with the trust and kind of privacy considerations that go into having an identity, proving an identity, storing details of identities in places. So it can also, ZKPs can also help with verifying computation, right? So we're going to take a look at how these ZKPs can do that. And so to understand how zero knowledge proofs can help with all these use cases that we've just looked at, we're going to take a look at what zero knowledge proofs are, right? And so it kind of works like this, right? I can run a computer program, and I can give you the proof of that I've run it, right? And so here's the output of the program, and I can prove that I've run a specific program with certain inputs, and then you can check this proof efficiently. So the actual checking of the proof, the computation does in constant time, which is obviously fast. So if you know about computational complexity theory, if computation scales with the kind of the size of input or other things, then it can end up being very computationally intensive quite quickly. But checking the proof is constant time, so it's always quick. The proofs are a fixed size, and you don't have to see the inputs that I use to generate the outputs, right? Unless I choose to give you those inputs, right? So we have these things called constraints, which are something that you have to kind of consider when you're making apps. But basically, in this way, I can prove that I've executed a program. I don't have to give you the inputs, and you can verify that proof very, very quickly. So that means, as I said before, right, you can use this as a developer to provide scalability. You can verify things. You can provide your users with privacy, depending on how you configure these proofs, and also security. So this is a slide. We actually also sometimes use an analogy of the Where's Wally or Where's Waldo game. So in America, it's called Where's Waldo. And in the UK, I know it as Where's Wally. I don't know if you have it in India, but basically it's a kind of comic book thing that you get. And there's these giant pictures with lots of detail. It's set somewhere like, a beach, or here they are at a theme park, or they're in a jungle or something, right? And there's loads of these wee characters. There's loads and loads of stuff going on. And the game is that you have to look and find a character who is dressed in a way. He's got a stripy jumper on, and he has glasses and like a walking cane. So you have to find him, right? And so you look at this game, and you see all these things going on, and then when you find the character, you've won the game, right? That's the end of the game. So if you think about how you can prove to someone else that you have solve the game, you could show them the picture, right? And then you could just point at where the character is, Wally or Waldo, and then that would prove to the other person that you know where Waldo is. But they would then know where Waldo is as well, right? So you've just given up the answer to the game. So one of the ways that we can think about a zero knowledge proof is if you take a giant piece of cardboard, so say you have a Where's Waldo puzzle and it's A4 standard size of paper, right? If you take a huge giant piece of card, right, and then you put that over the Where's Waldo game, and then you cut out a tiny little hole that just shows you the Wally character, but nothing else, right? So you're kind of putting a mask over the game. You can then show that to this other party. They'll see, okay, you found Waldo because I can see the character through this giant piece of card, but I don't know anything else about where Wally is on the map, right? So if I give this person the game, then it's going to take them a while to find Wally, right? So in that way, you can kind of think about a zero knowledge proof. You can prove to someone that you know something without giving them the actual piece of information that you know, right? The actual answer. So this slide here is kind of taking a look at zero knowledge proofs and comparing them to other cryptographic primitives that you might be familiar with. So for example, a hash function, right? I don't know if you can see my cursor, but I'm kind of wobbling it around things that we're talking about. A hash function takes in some data, right? And then it outputs another piece of data that is not related, right? So it's kind of a big, it's a fixed length string. And if you put two pieces of data into the hash function that are exactly the same, it'll give you exactly the same output, right? So a hash function can help you verify the integrity of data. You can say piece of data A is the same as piece of data B by putting them through the hash function, right? You can use public key signatures. So a public and a private key pair you can use. So you can use the private key to basically sign some message or a piece of data that produces a signature. So then if you give somebody else this message or this data and the public key, they can verify, you know, with the verification function, okay, this signature means that this piece of data has been signed by that private key, right? So in that way, you can, you know, verify the kind of provenance of data because someone has signed it or a website has given you some piece of data that's been signed by their certificate or their key. So you can be assured that it actually came from some source, right? So zero knowledge proofs, when we're looking at using them with Mina Protocol, right? You take your program, okay, some logic that you want to implement in your app, and then you do this compile step, which is the first one here, and that generates something called a verification key. So that's a kind of cryptographic representation of your program. It's a bit like a hash in the sense that it's a kind of string of data that doesn't really have, you know, people can't get any kind of data out of it. It's this kind of string of effectively, you know, if you look at it, you'd be like, that's gibberish. But then what you can do is now you can give somebody else. So in this compile step, you generate something called a prover function, right? So when you give somebody else this program, they can run the prover function. So they run the program with your kind of logic that you're giving them as an app. They put some public inputs and some private inputs into it. And then when they run this prover function, that produces the proof, right? Which is a string as well. So what you can then do is run the verification step, which is you take the proof that that the user generated when they ran your code. They take the public inputs, but not the private inputs. And they take this verification key that you generated initially when you made your ZK app. And that gives you like a yes or a no. This proof is either valid or it isn't. So in that way, you can write a computer program. You can give that program out. So you as a developer can give an app to all your users, they can run your app with whatever inputs they have, and then someone somewhere, could be you, could be, in the case of the Mina Protocol nodes on the network, they can verify the proof that this program was run, right? But they don't have to take the program, verify its source code, get all the inputs that your users use, and then run the program again to verify that it was run, right? And to verify the output. So it's this idea of generating a proof and then using the proof to verify that the app ran, the ZK app in this case. So now we come to Mina Protocol, which is a layer 1 blockchain that's built entirely from the ground up on ZKPs, right? Zero knowledge proofs. So we've just learned that zero knowledge proofs have great applications for scalability and privacy. So one of the things that Mina leverages, that uses these ZKPs for, is as I said, right, the verification of these proofs is very fast and very efficient. So that actually means that you can verify the Mina blockchain on using not a lot of computational power, right? So you can verify the Mina blockchain on different kinds of devices. For example, mobile devices. You don't have to have a server or a mining farm to be able to verify the blockchain. And it also uses this idea, which is a really cool thing that has been implemented because of the cryptography in Mina. It implements something called recursion, right? Which is a really cool concept where you can take a proof, so you can verify that computations happen. You can take that proof, this string, and you can include that in a new proof, right? So in that sense, you can chain together proofs and kind of chain together computation and things that have happened in particular orders, right? Via the kind of cryptography that Mina uses. So this diagram in the middle here shows the ZK snark, which is the kind of proof that we're talking about. You can include those snarks in future generation, when you generate snarks in future, right? So this is kind of the idea of, and this is how the blockchain runs and can be lightweight, is that you can include the proof of the entire blockchain up to a certain block in the next block. And so basically, if you think about including proofs into other proofs, you can take two proofs and collapse them down into one proof, right? And so developers who have worked with binary trees before may recognize that pattern. So you take two proofs, collapse them into a single proof, and then you can collapse that into a single proof with another proof, right? And so you kind of end up with this binary tree. And so the root of that tree is what's called the state proof, and you can verify that very quickly. So you can verify the whole blockchain with just a few kilobytes, which includes the state proof. And also it's efficient because it's constant time to verify the proof, right? So in that way, Mina kind of links the blocks together with these proofs, and that means that it can have a very lightweight and efficient verification compared to other blockchains, right? And also another thing as well about having these proofs that are small, that are lightweight, that are quick to verify, is that you can make ZK apps which are interoperable, right? So you can take a proof that you've generated with Mina Protocol and the cryptography that it uses, and then you can kind of verify that on Ethereum, right? So then you can write a huge ZK app that does lots of computation, right? And then you can produce a simple proof that you can then pass into an EVM smart contract. The EVM smart contract can verify that, and then you've got a kind of de facto ZK layer for Ethereum or other EVM smart contracts, right? So in that way, it's interoperable. And so these aren't just things as well that we're kind of talking about, right? This the NIL Foundation is a kind of software development group, right? Research group, and they've been awarded a joint grant from the Ethereum Foundation and from the Mina Foundation to build this in EVM Mina state verification functionality, right? And so that's currently in testing. And so yes, it's that's been having a lot of work done on it for quite some time, and we're excited to see the results. But basically, you know, you can write a load of computation to do via a Mina ZK app, and then you can take the proof that it generates, pass that into an EVM smart contract, and then you can verify that the computation has happened without doing it in an EVM like smart contract environment where you'd have to pay gas fees for the computation you do, right? So that's really exciting. And then when it comes to the succinctness and the fast verification, this is Open Mina, where it's actually a in-web browser node that you can spin up, right? And you can, so a user, for example, could verify their account and send transactions to the network, right, directly in their browser, rather than having to go through a third-party service provider who run nodes or something that submit transactions to the blockchain, right? So these are really cool things that are happening that are really exciting. And so I've been talking about the cryptography a lot, right? And how it powers the Mina blockchain and the Mina protocol. Now, I've also mentioned ZK apps, and so this is something where we've made the cryptography available to developers, right, to build their own apps that use zero knowledge proofs, right? So we use it on the Mina protocol side to run the blockchain, right, and to have this succinctness and this efficient proving. And now we're kind of throwing it out there and saying to developers, right, here you go, here's the tools, let's see what you can build with it. You know, whatever ideas you have, come and try and do them with the tooling. So to understand how you can build ZK apps, right, it's good to consider from to kind of compare it to other blockchain models that you might be familiar with to start with. So we've talked about the EVM, right? And so the EVM uses on-chain computation. If you've ever done any EVM development, you'll probably be familiar with this. So some user wants to use a smart contract, and so, you know, they use some sort of app, probably a web app. They create they call a smart contract function that they want to use to update the state or do some sort of transaction or something, and then that gets passed to the Ethereum network, and then the nodes on the Ethereum network run the smart contract. They all have a copy of the smart contract. They all run the compute, and then you have to pay gas fees. So the more computation you do or the more storage you use, the more you have to pay in gas fees, right? Because of, you know, so we're verifying the computation by all the nodes on the network running the same computation, getting the same result, right? So that's where the verification comes from. Now, Mina, right? The Mina protocol, ZK apps use off-chain computation and then on-chain verification. So we're kind of stitching together some concepts that I talked about over the last few slides. So basically, your user runs your ZK app in their browser, right? So they run all the code client side. So they do all the compute on their local environment, and then they run that, what I was talking about, the prover function, right? So your ZK app, they run this ZK app, they run the prover function, and that generates this proof, right, which is a string. So then all you have to do is send a transaction to the network with the state updates that you want to make, or the transaction or whatever, and you include the proof, right, that you've generated by running the ZK app in the transaction, okay? And then the nodes on the Mina network, they take the transaction, they verify the proof, and then they apply, you know, the changes to state or the transfer, you know, the transaction that you want to do, okay? So you run the code locally, you generate the proof, and then the proof is verified on the network. So all you actually do there, right, is you send a transaction to the network and you pay a transaction fee, but you can do as much compute as you want. You don't have to pay extra, you know, you don't pay gas fees based on how much compute you do. You just pay a transaction fee based on the cost of block space at the time, right? So that's quite a kind of paradigm shift. So we've shifted all the computation off the network to the local machine, and then we're just verifying the proof of this computation on the network, right? And then so you're just sending one transaction. So first of all, this is good, right? You can really offer your users more privacy, because you can keep computation and data client side, and you can give them, your users, more choice, or you as a developer have more choice about what data to keep private and what data to expose publicly. There's no gas costs through this kind of succinctness. So you produce this proof that, as I've said, is succinct and quick to verify. You don't have to repeat all the computation everywhere. So the cost doesn't scale with computation. You just have to pay for a transaction. You can kind of compose. So using this idea of producing these proofs for large amounts of computation, right? You can get kind of scaling as well, right? So you can do large amounts of computation, and you can write your own ZK apps to use this concept of recursion to really get like higher scalability for doing these kinds of tasks. And also you can get this idea of interoperability. So, you know, the idea is you write a ZK app, you produce a proof, you verify that proof on the Mina network, and then you can use that proof, right? And you can verify it elsewhere as well. So in that way, you can kind of because this proof again is fast to verify, and it's lightweight, right? It's just a fixed size. You can verify it in other places. So you can verify loads of compute or things that are happening with your users or your ZK apps on Mina. You can just verify that quickly in other places, right? So in that way, yeah, as I said, right, Mina kind of becomes a default ZK layer for wherever you want to interoperate with. So we're going to go into a bit more detail about how it works, because I explained that the network verifies the proof that you produce, right, when your users use your ZK app. So just to let you know how that works, I said before when we're taking a look at ZK proofs, right, when you compile, you know, you generate your ZK app, you create this thing called a verification key. Okay, and so basically what happens is when you deploy a ZK app, you write your code, you build your code, and then you send when you build your code, you generate this verification key. So when you deploy a ZK app, you create a new account on the Mina network. That's a ZK app account, and then you send the verification key that gets generated to the network, right? And the verification key gets stored against your ZK app account. So then when people use that ZK app in future, right, they use your code, they run the program with whatever data they have, whatever inputs, they create a transaction which includes the proof that they generate when they run the ZK app, and that goes to the Mina network. Now the nodes in the Mina network will say, okay, this person is using that ZK app. That ZK app has this address. Here's the verification key, right? So you as the developer, you build your app, you send the verification key to the network. Now, the user generates the proof, and then the nodes on the network check whether that proof is valid or invalid using the verification key that you stored, right? So if someone, for example, uses code, tries to use code that you've not written, right, then it doesn't create a proof that's valid with the verification key stored on the network. The verification key that you stored will only verify proofs with the exact code that you wrote with the ZK app, right? So in that way, you have you don't need to store the code on the network. You have the verification key. If the code changes at all, if you know, someone does a man-in-the-middle attack, or the user tries to you know, game the system, change something, you know, hack the smart contract and generate some sort of result they're not supposed to, then it just won't produce a valid proof, and the verification key is on the network, right? So in that way, you can, so that's how it works, right, with this key. And in that way as well, you can kind of be assured that you're running the right ZK app as well, because the proof will be valid against the verification key. And so the kind of structure, when you want to build ZK apps, you have to think in terms of methods. So a method of a ZK app is something which creates a proof, right? And so you can have multiple different methods in a ZK app. You can kind of think about them a bit like functions in other blockchain programming paradigms. So you can call a method on a smart contract, you give it some input. There's some smart contract state on chain. There's a very small amount. You can store a very limited amount of information in there, but there's kind of ways that you can use cryptography to store data elsewhere and keep the state of that data in this state storage in the smart contract. And then there's, you know, some state in the rest of the world, right, that you have as a developer, a database or you know, a list or whatever. So when you call that method with the arguments, that results in, you know, if it's you know, you're running the right code and it's a valid proof, then you can update the state of the smart contract and you can update something somewhere else, right? So that's kind of how ZK apps are structured. It's these methods. That's your smart contract, right? It's made out of these methods. And so if you want to learn how to write these methods, now we need to talk about Snarky.js, right? And so Snarky.js, it's a TypeScript library. Some people, you know, there's kind of mixed opinions on whether it should be called Snarky.ts or not, but for now it's called Snarky.js. It's a TypeScript library, and you can use that to define zero knowledge proofs, right? So what that means is you can use Snarky.js to access the cutting edge cryptography that powers the Mina protocol to build your own apps that use ZK proofs without having to understand in a kind of deep technical level the math, the cryptography, and the kind of engineering, the functional programming that goes into building zero knowledge circuits and proof systems, right? So the point of Snarky.js was to expose this cryptography and kind of the proof system to developers to be able to use easily to build useful ZK apps, right? Useful applications. It's got good integration with tools and things that you'll be used to using. So it's in TypeScript. It's got good integration with IntelliSense on VS Code, and kind of out of the box integration with NPM, Prettier, ESLint, and Jest for testing. So these are obviously the logos on the screen. So it's kind of, it's meeting you where you are, and there's tools that you're already used to use. Getting started really is as simple as taking these 5 steps, which is you install the CLI tool. The CLI tool actually has a lot of kind of boilerplate and scaffolding. So you can use that. ZK project creates your project. You go into the directory of your project name. You do some config, right? And then you're ready to deploy your ZK app. But there is also a step where you have to request some testnet tokens from the faucet. But then after that, you're ready to deploy your ZK app, right? And you can kind of check it out and see how things works. Oh, it is probably important to mention as well, we are currently live on testnet with ZK apps, and there is a hard fork coming, which will basically introduce this functionality, the ZK app functionality, onto the main Mina network. But for now, we are working on the Berkeley testnet for ZK app functionality. So I mentioned earlier as well this idea of recursion, right? And so we're just going to kind of take a bit of a closer look at that concept, because it's one of the things that really differentiates Snarky.js, right? allowing you to do some really cool things. Now it says here, Snarky.js lets you define, create, and verify ZK snarks with infinite recursion. So ZK snarks are the proof. So when I've been talking about zero knowledge proofs, ZK snarks, that's the type of proof we're talking about. When we say define, that's you as a developer writing a program that defines the proof, right? It defines what people need to do to produce the proof, and it defines what the proof actually proves, right? Creating the proof is when your users use the ZK app. You've defined the rules of the proof. They create the proof according to those rules. And then verifying the proof is when someone takes the proof and says, checks it and says, okay, this proof is valid for the set of constraints or this program, this ZK app that we're talking about. Now, recursion is the concept of taking those proofs and including them in another proof that you generate, right? So we've got an example here, which is a card game. Obviously, everyone's got the, is that a royal flush? I think it's the best hand you can have in poker, right? Where it's like the cards are all the same suit and they go in this, like the order of like the 5 cards, and then it's the highest cards you can have. So all the players have the strongest hand in poker. So presumably they're not playing poker, they're playing some other game. But the way you think about it is you as a developer have written a ZK app with some logic for this card game, right? And so player 1 can take your ZK app, can play their turn in the card game, and they can then produce this proof, right? So they produce a proof using the prover function, using your ZK app, and the verification key is stored on the network. Now, they take that proof and they send it to player 2, right? So player 2 takes the proof that player 1 sent them. They can use the verification key on the network. They can verify the proof. What the proof says is player 1 has taken their turn in a valid way according to the rules of the game. So then player 2 can make their move. They can then produce a proof that they've also taken a valid turn, but they include the proof that player 1 sent them. So now player 3 can look at that proof. They can verify that player 2 took a valid turn, but they can also verify that player 1 took a valid turn before that, right? So then, as you can imagine, the proof stays a fixed size, no matter how many turns you do, and the proof always is fast to verify. Okay, so in that sense, you can imagine infinite number of turns between these players. The players are always aware, can always verify that the game is taking place in a valid way. And then also you could imagine, right, this whole thing could happen off chain. So you can kind of use recursion to chain these proofs together. And then when you want to report the result of the game, you can post that proof on chain, right? And so then anyone who has access to the blockchain can take that proof and say, wow, look at this. All these proofs are this kind of, the run of the game was all valid. And here's the end result, which is this proof, which is on the blockchain. I can go and look at that and verify it. So in that way, right, this is an example that we use, and we're really excited for developers to think about how you can apply that concept of off-chain verification, or these kind of counterparties who may not trust each other but use the zero knowledge proofs to verify that things have happened in the correct way. Right. So that's something that's really cool about Snarky.js. I hope that I've explained it in a way that you can understand. And there's this kind of recursion API in Snarky.js, which you can use, which makes it kind of a bit easier to get your head around and to start kind of building stuff with, right? This is the image that we saw before, right? And it just is kind of reiterating that concept of, here's a proof, which is the ZK snark. Now we can put that into a new proof, and then the proofs are kind of linked together, right, via this kind of recursion concept. And so I hope that was a good quick introduction to Snarky.js and how you can build your own ZK apps. I hope that your kind of your interest has been piqued and that you want to find out more, because I'm about to tell you the next steps that we can take and some things that have been happening in our ecosystem. So the first thing to mention is ZK Ignite, which is a program that we are running to provide builders with support. So it's a grants program where you can kind of receive funding or a grant for your project. And there's also community support from mentors and some workshops and things that we do. So it's a program that lasts a number of months. The idea is you kind of have an idea for a project, you write a proposal for it, then there's electors who kind of are a bunch of people who are selected from the community who vote on the proposals that they want to see be accepted into the program. And then if your project is accepted, then you kind of get allocated mentors who will help you reach your milestones and build your project across the program. So that's something which is really exciting. We've just kind of, we're in the process of running Cohort 1, which is the first group of projects that were selected to participate in the program, and we have Cohort 2 starting soon. So I think it's starting in July. The main thing to say about that is, as well, you don't have to have any kind of idea before you turn up to the first sessions. There is time in the program allocated to have people be introduced to the technology and to discuss ideas, to form teams, and also to write draft proposals and get feedback on them. So you kind of have this chance of writing a proposal. It's not just like submit that and then you get a yes or a no. You write the proposal, you get feedback from the electors who are actually going to be voting, and then also there's feedback from anyone in the community and other builders, and then you can submit your final proposal, right? So there's what I would say is, if you're interested, you should sign up and go to the introductory sessions, even if you don't have a firm idea if you want to participate or what you want to build, because there'll be lots of other people there who probably are in the same circumstances. And there is supposed to be a QR code on this slide, which I have not included, but I will probably put it in towards the end. And that's got like a sign up link for you. I also was going to just take a quick look at a few of the projects that we've seen come out of ZK Ignite Cohort 1. So there's one called Anomics Network, which is a really cool ZK rollup based layer 2 solution on top of Mina Protocol, which gives a lot of scalability and privacy. So that's really cool. There's something called a keyless wallet, which one of our community members has been working hard on, and it kind of uses social recovery and this idea of Shamir secret sharing, where you kind of split some of these secret data pieces amongst parties that you trust, and then you can only kind of recover the secret if you have a certain amount of them, right? So it kind of gives users a different UX when it comes to blockchain, because they don't have to have this private key, and also they can recover their account if they lose access to it using this kind of system where they store secrets in different ways using these zero knowledge proofs. So that's really cool. And there's also excuse me, there's also something called bio snarks, which is applying zero knowledge proofs to the kind of biotech industry and helping data sharing and validation. So that's a really cool project as well. So hopefully that will give you kind of an idea of what kind of projects were accepted into the program, and maybe kind of set some ideas off in your brain. This is quite a detailed slide with a lot of the projects that were funded via ZK Ignite Cohort 1. I think we're going to make these slides available to you so you can look over these. And also, if you sign up for ZK Ignite on the kind of website that we're going to link you to, you can see all of these projects in more detail, see their proposals, and see what progress they're making as well. So there's lots of really cool projects. Here we go. Right. So I knew there was a QR code somewhere. I think the June 14th date is out of date, and I think it's actually starting 2 weeks later now, but I will double check. But if you scan that QR code, it will tell you the right date for sure. And so that is the sign up link for ZK Ignite Cohort 2. Again, if you're interested at all, you can sign up for that. You'll get updates about what's happening, including invites to the sessions when they start. And again, you can go to the introductory sessions, you can find out more. You don't have to go, there's no obligation to even go, you know, to anything. You can go to the first one and decide you don't want to do it. And also you don't have to have any ideas in mind. You can turn up with nothing and kind of go from there, right? I highly encourage you to do it. It's good fun. There's a lot of cool, innovative, interesting people who get involved. And also it's run by our amazing community team who really keep the enthusiasm and energy high. Now, there's also, you can look now as well, we have a multi-year roadmap for the protocol available on the website. So it's actually interactive as well, which I think, have I just lost functionality? I might have. Here we go. Right, I'm back. The roadmap is available on the website. It's split into 5 key focus areas, including ZK programmability, settlement layer performance, the road to DAOification, trust minimization, and the Minaverse. So if you want to find out more about those things, you can look on the roadmap. I think it will be linked on a QR code, which I'm going to give you shortly as well. And the cool thing about the roadmap is it's actually interactive as well. So you can click on these areas, find out what the things on the roadmap are that we're going to be working on, and find out what kind of progress we've made so far, and what progress we're making at the moment. So this is a QR code for all the next step resources you need. It's got some links there to the quick start guide. I believe the documentation. I'm actually going to scan it quickly just so I know exactly what I'm talking about. I scanned it earlier and I thought I'm definitely going to remember what this is, but I didn't. So here we go. It links to the Mina website, the Discord server, and the Mina India community channels, which is the Telegram. There's a Twitter account, and there is a Medium blog. And so that roadmap that I was talking about will be on the website. And there's also links to the documentation on the website where you will be able to find more information about doing ZK app development, about the Mina protocol. There's some good tutorials there as well to kind of step you through things and illustrate concepts, so some more advanced concepts when it comes to ZK app development. So I would advise you to take a look at them if you're interested in kind of getting started and hacking on ZK apps. I think as well, it's important to mention that please do join the Discord server if you're interested and want to get involved more. We have a lot of channels that focus on specific things on the Discord server. I think there's an Indian language channel or kind of regional channel, but I'll have to double check. But also for ZK app development, there's a couple of channels on there where people kind of discuss things and bounce ideas off each other. There's also a Q&A channel, so you can go and ask your technical questions there, and you can search questions that people have asked already. That's really useful as well for developers, and there's some people on there who are really helpful, friendly, and responsive if you're looking for technical information and answers. And there's also office hours where Mina Foundation and O1 Lab staff will be available in the kind of voice channel, and we also get on the cameras and have kind of a hangout hour where people can just turn up, ask any questions that they have. So yeah, that's that QR code. And now, thank you for listening. I finally got to the end of my presentation. I hope it was useful for you, and I believe we have some time for questions, if there are any.
Yeah, we have decent number of questions, and first of all, thank you so much, Angus. I think this is terrific. A very great simple explanation about what a zero knowledge is and the amazing things Mina has been building. So, guys, would encourage everyone to go and apply for ZK Ignite. You can always form teams. This is the greatest technology innovation that is happening in the blockchain space, and I highly recommend you to go ahead and explore. So on that note, Angus, I think we have a couple of questions, mostly around technical stuff. Marty, let me go through a couple of them. So the first question is, what is the difference in block components compared to Ethereum?
In block, what is this one of the block components compared to Ethereum? Now that is a good question. I am not too up to date with the exact structure, although a block is it's similar in structure to a block that you might see in Ethereum. There's there's a block header with some metadata, and indeed, so if you're familiar with the way that the hashing chains blocks together in Bitcoin or Ethereum, so the state proof, which is not a hash, but it's a string that comes out of a cryptographic operation, right? Which is this generating a proof that we've been talking about. So the state proof, it looks the same, right? It looks like a string, and so that's in the block header as well. And then there's transactions in a block. I'm not sure exactly what format they are in, but also I can point you to a block explorer, which will let you take a look. There also might be some documentation somewhere that I can find as well about the exact structure of a block. But then if you're looking for to like poke around in the block to see what kind of stuff is in there, I can point you to a good block explorer, which will let you, take a look inside these blocks.
Cool, awesome.
Cool. Thanks.
Yeah. So the second question was again more of a tech one. So how do we define if a function parameter, whether it is a private input or a public input, for a given contract?
I was on mute. I've just posted the link to Mina Explorer, which is the block explorer I was just talking about. And I'm going to read through this question again. How do we define if a function parameter is a private input or a public input, say for a method for a given contract? Private input isn't something which is available on chain, and public inputs being something visible on chain. So yes, so there's inputs that you provide to methods. All the inputs, the arguments for methods are private by default. So so it's basically, I think I might be able to take a look. I might not actually, because it might be a bit clunky, but essentially when you kind of declare a method's arguments, you can say whether they're private or they're private by default, but you can say, oh, here's one which is public, right? And also you can store things that you want to keep public in the state storage, but private, the arguments are private by default, right? So then as a developer, what you have to think about is, what information do I actually need to make public for the proof to make sense, or for like me to be able to prove something? So one of the things that a good example to illustrate this, I may even have it actually in this deck. I don't think I do. But it's just a diagram, right? But if you think about a Sudoku puzzle, you start off with the puzzle and it's got some numbers in it, but not the solution, right? It's not filled in with all the other numbers. Now, if you want to make a ZK app that proves whether someone has done a Sudoku, you need to have an input for them to put their solution in and check it to make sure that it's a valid solution. So that's the ZK app that runs client side. So you keep their solution private, but then you say the public input is the actual Sudoku puzzle. Because if you just have a proof that says someone has solved a Sudoku puzzle, then, you know, what can we do with that? What does that mean? So then if you provide the actual the Sudoku puzzle without the solution as a public input, then this proof will say, here's a Sudoku puzzle. This person, this user has a solution for it, right? Has solved it. But then that you don't have to give them the actual solution. So then the proof makes using the puzzle as a public input, the proof makes more sense, right? It says something. It says, here's a puzzle, this person has solved it, right? And so you kind of need to, it's a bit of a different way of thinking about things. But yeah, using these private and public inputs is how you make these proofs kind of make a bit more like sense, right? You've got to think about what do you prove rather than just what are we computing, right? How do we play the game?
Awesome, thank you. So there are two to three more questions there. So primarily the next one is, how is the verification key generated?
That's a good question. It's called the verification key. It's not actually a key. It's a string, and it is kind of a low-level cryptographic representation of enough data that you need to verify the proof. Now, what that means is, in practice, the verification key is generated when you, as a developer, build your ZK app, right? So when you run the ZK app, it produces a proof. And wait, so when you build the ZK app, it builds something called a circuit, right? And this also produces the verification key. So this is quite low-level stuff that you don't really need to understand in too much detail. But the verification key is generated by this thing called the proof system, right? And so you write some logic, it gets made into a circuit and a corresponding verification key, and that's kind of like lower level cryptography stuff. And so to understand that sort of thing, you need to have quite an in-depth knowledge of cryptography, and also probably like cryptographic software engineering, which are both quite complicated and involved topics. The good news is, though, Snarky.js really does abstract all of that away from you. So you don't really have to understand how the verification key is generated. You just need to know that it gets generated at build time when you build your ZK app. And then you can use it to verify proofs that people produce when they use your ZK app, right? Once it's built.
Oh, awesome. Thanks a lot for that. So we'll take this one last question. Where is the Mina token balance of every holder stored? So it's like, what is the state in which the token balance is stored?
Yes. So where the state is stored. Now, that's a good question. Oh, there's another good question from Gunjan as well. I'll answer both of them, right? The first thing is, where is the Mina token state stored? Now, we talk about the succinct blockchain, and it's only a few kilobytes. The fact is that you can verify a single account balance with a few kilobytes. And so as a user, to verify your account, you only need a few kilobytes on your phone or on your laptop, right? To be able to verify your account and then send transactions to the network via this kind of web node thing or a similar idea in future. Now, the token balance are actually token balances are stored against your account, right, in some state storage, and I think there is, you know, basically like a giant Merkle tree that stores all the account balances. This is also a good question to ask on the Discord, right? Because there's a lot of people who know a lot about the blockchain side of it. I mainly focus on the ZK apps side, but essentially there's kind of a little storage field that says, you know, that holds your Mina balance, and indeed, right, there is if there is also that's how the kind of the custom tokens API kind of works as well, is that you kind of create a new you get a new storage state container on the network to keep your balances of other custom tokens as well, right? And so when all this, the data has to get stored somewhere, right? And so when you interact with the blockchain as a user, you can have this succinct blockchain, but then if you're running a blockchain node, you know, the nodes have to store more information, right? So people running nodes that participate in like network consensus, block production, archiving the blockchain data, they'll be running, you know, more like high performance computing equipment, right, that require more storage, and they can store that data, right? So yes, and there's a good answer in the chat. I think I've not taken a look at it, but I saw Gunjan asked, do we need trusted setup per dApps, or only one universal one, or none at all? So this is a very good question as well. A lot of material that is out there, if you want to read about the specific kind of zero knowledge proof that we're using, the ZK snark, a lot of material says you need a trusted setup for, you know, for a ZK snark, right? And so there have been other pieces of technology that use snarks that do this kind of ceremony, or, you know, there's one that in the Ethereum ecosystem that's doing kind of an infinite, never-ending powers of Tau ceremony where everyone can kind of contribute to it, right? This trusted setup. But the thing is, in the Mina protocol, there actually isn't a trusted setup required for each snark. That's the only really way that the blockchain could work, because there's so many snarks happening, and it comes down to some innovation that the cryptographers and the software engineers have done at O1 Labs, where basically they use a combination of the inner product argument and some other kind of bits and pieces to avoid the need for a trusted setup effectively. And so you can read more about that. I think there's maybe some documentation about it in something called the Mina book, which is a kind of separate website from the developer documentation that goes into a lot more detail on the mathematics side of things. But it's basically some kind of configuration of maths, including using this thing called the inner product argument, which I believe bulletproof. There's a cryptographic thing called a bulletproof, which also uses this, which avoids the need for a trusted setup for every single snark that you use. So like per transaction, per DApp, etc. So we don't need to do that. So that's something which is pretty cool about Mina as well. So yes, thanks for answer. No problem.